Picture this, a vast, silent expanse where planets dance around a fiery star and moons glide through the darkness like silent sentinels. Yet, despite centuries of exploration, our solar system remains a treasure chest of secrets, each one more baffling than the last. What if I told you that some of the most fundamental questions about our cosmic neighborhood still have no answers? From the eerie darkness of Mercury's hidden side to the swirling storms on distant gas giants, mysteries abound in every corner of our solar system. Today, we're diving into 25 of the most perplexing enigmas that continue to stump scientists and ignite our imaginations. These aren't just questions about space, they're clues to understanding our place in the universe. So, buckle up and join me as we unravel the unsolved mysteries of the solar system, where every discovery raises more questions than it answers. By the end of this journey, you'll see the cosmos in a whole new light, and you might just find yourself wondering what else is out there waiting to be uncovered. Let's begin. Now turning to the first mystery on our list, we find ourselves staring at Mercury, the closest planet to the Sun. But here's the twist. While one side of Mercury bakes under the Sun's intense heat, the other side remains shrouded in perpetual darkness. And this dark side isn't just dim, it's significantly darker than the night sides of other planets. Why is that? Scientists have been scratching their heads over this for decades. One theory points to Mercury's surface composition. Unlike Earth or even the Moon, Mercury's dark side is covered in a layer of graphite, a form of carbon that's incredibly dark. This graphite might be the remnants of an ancient crust that formed when the planet was young. Another factor is the lack of sunlight. Because Mercury is so close to the Sun, its rotation is locked in a way that one side always faces away, leaving it in eternal shadow. Without sunlight to reflect, the dark side stays eerily black. But here's the kicker, even with these explanations, the exact reason for its extreme darkness remains a puzzle. Could there be other materials or processes at play that we haven't discovered yet? As we move forward, this mystery reminds us that even the planets closest to us hold secrets that defy our understanding. Now turning to the next mystery, we shift our gaze to Venus, Earth's so-called twin, but with a twist that makes it anything but hospitable. Venus is a planet of extremes, and its runaway greenhouse effect is one of the most baffling enigmas in our solar system. Despite being similar in size to Earth, Venus is a scorching inferno with surface temperatures hot enough to melt lead. So, how did this happen? The answer lies in its atmosphere, which is a thick, toxic blanket of carbon dioxide and sulfuric acid clouds. These clouds trap heat so effectively that Venus has become the hottest planet in our solar system, even hotter than Mercury, which is closer to the Sun. Scientists believe that billions of years ago, Venus might have had oceans and a climate similar to Earth's, but something went terribly wrong. Volcanic activity may have released massive amounts of carbon dioxide into the atmosphere, triggering a feedback loop where the planet's surface heated up, evaporating any water and releasing even more greenhouse gases. Over time, this process spiraled out of control, creating the hellish environment we see today. But here's the real mystery. Why did this happen to Venus and not Earth? Both planets started with similar ingredients, yet their fates diverged dramatically. Could Earth one day face the same fate, or is there something unique about Venus that sealed its destiny? As we explore this mystery, it serves as a stark reminder of how delicate the balance of a planet's climate can be. Now turning to the next mystery, we venture into the asteroid belt, a region between Mars and Jupiter that holds clues to one of the solar system's most intriguing puzzles, the missing planet. The asteroid belt is a vast collection of rocky debris, but scientists have long wondered if it was once home to a fully formed planet. The theory suggests that billions of years ago, a planet-sized object may have existed in this region, only to be destroyed or disrupted in some catastrophic event. But what could have caused such a dramatic transformation? One leading idea is that gravitational forces from Jupiter, the solar system's largest planet, played a key role. Jupiter's immense gravity could have destabilized the orbit of this hypothetical planet, pulling it apart or scattering its remains into the countless fragments we see today. Another possibility is that the planet never fully formed in the first place. During the early days of the solar system, the region between Mars and Jupiter may have been too chaotic, with collisions and gravitational interactions preventing a planet from coalescing. Instead, the material in this area remained as smaller bodies, eventually becoming the asteroid belt we know today. But the mystery doesn't end there. Some scientists believe that remnants of this lost planet might still exist within the asteroid belt, hidden among the rocks and dust. Could one of these asteroids be a piece of a long-lost world? As we explore this enigma, it raises fascinating questions about the formation of our solar system and the forces that shaped its evolution. What other secrets might the asteroid belt hold, and could they help us piece together the story of this missing planet? The search for answers continues, reminding us that even the smallest fragments of space can hold the key to understanding our cosmic past. Now turning to the next mystery, we shift our gaze to Mars, the red planet, and one of its most baffling enigmas, the disappearance of its atmosphere. Billions of years ago, Mars was a very different world. Evidence from its surface suggests it once had rivers, lakes, and even oceans of liquid water. But for water to exist in liquid form, Mars must have had a much thicker atmosphere capable of trapping heat and maintaining pressure. So, what happened to it? The answer lies in a combination of factors, with solar winds playing a starring role. Unlike Earth, Mars lacks a strong global magnetic field to shield its atmosphere from the sun's relentless stream of charged particles. Over time, these solar winds stripped away much of Mars's atmosphere, molecule by molecule, leaving behind the thin, cold air we see today. But that's not the whole story. Volcanic activity and massive impacts may have also contributed to the loss, releasing gases into space or altering the planet's climate. Today, Mars's atmosphere is less than 1% as dense as Earth's, a stark reminder of how fragile a planet's life-sustaining systems can be. Yet, the mystery deepens when we consider the evidence of ancient water. How did Mars maintain liquid water for so long with such a thin atmosphere? Some scientists believe the planet may have experienced periods of atmospheric replenishment, perhaps through volcanic outgassing or comet impacts before losing it again. Others suggest that Mars's water may have existed in shorter, more transient bursts tied to its climate cycles. As we explore this puzzle, it raises profound questions about the fate of other worlds and the delicate balance required to sustain life. Could Mars's story hold clues about the future of our own planet? The search for answers continues as missions like NASA MAVEN probes study the remnants of Mars's atmosphere, piecing together the story of its dramatic transformation. What other secrets might the red planet reveal, and could they help us understand the broader mysteries of planetary evolution? Now turning to the next mystery, we journey to the largest planet in our solar system, Jupiter, and its iconic Great Red Spot. This massive storm, larger than Earth itself, has been raging for centuries, captivating astronomers and sparking countless questions. But in recent years, something strange has been happening. The Great Red Spot is shrinking and changing shape. Once a colossal oval stretching over 25,000 miles wide, it has now narrowed to about 10,000 miles, and its once precise edges have become more irregular. What's causing this transformation? Scientists believe the answer lies in the complex dynamics of Jupiter's atmosphere. The Great Red Spot is essentially a high-pressure storm, spinning counterclockwise and surrounded by powerful jet streams. These jet streams, which flow in opposite directions, may be eroding the storm's edges, causing it to shrink and lose its classic oval shape. But that's not all. The storm's internal dynamics, including its swirling winds and interactions with smaller storms, could also be playing a role. Some researchers suggest that the Great Red Spot might be feeding on smaller storms, absorbing their energy and altering its structure in the process. Others speculate that changes in Jupiter's atmosphere, such as shifts in temperature or cloud composition, could be influencing the storm's behavior. What makes this mystery even more intriguing is what it reveals about Jupiter itself. The Great Red Spot is a window into the planet's turbulent atmosphere, offering clues about its weather patterns, wind speeds, and even its internal heat. By studying this storm, scientists hope to uncover the secrets of Jupiter's deep atmosphere and the forces that drive its chaotic weather systems. But the Great Red Spot's future remains uncertain. Will it continue to shrink, or could it stabilize and persist for centuries to come? Some models predict it could disappear entirely within the next few decades, while others suggest it might simply evolve into a new form. As we watch this ancient storm transform, it reminds us of the ever-changing nature of our solar system and the countless mysteries that still await discovery. What other secrets might Jupiter's swirling clouds hold, and how will they deepen our understanding of the giant planets? The answers lie in the winds of the Great Red Spot, a storm that has endured for centuries but may now be entering a new chapter in its long and turbulent history. Now turning to another astonishing phenomenon in our solar system, we shift our gaze to Saturn, the ringed giant, and its mysterious hexagonal storm. Nestled at Saturn's north pole, this six-sided storm is unlike anything else we've observed in the solar system. Its precise geometric shape, spanning nearly 20,000 miles across, has baffled scientists since its discovery by the Voyager spacecraft in the early 1980s. But what makes this storm so unique, and how does it maintain its perfect hexagonal form? The answer lies in the complex interplay of Saturn's atmosphere and its rapid rotation. Saturn spins so quickly, completing a full rotation in just about 10.5 hours, that its atmosphere is dominated by powerful jet streams. These jet streams, moving at incredible speeds, create a turbulent environment where the hexagonal storm has formed. Scientists believe that the storm's shape is a result of these jet streams interacting with the planet's rotation, creating a standing wave pattern that locks the storm into its six-sided form. What's even more fascinating is the storm's stability. Unlike most weather patterns on Earth, which change shape and intensity over time, Saturn's hexagonal storm has remained remarkably consistent for decades. This suggests that the forces shaping it are deeply rooted in Saturn's atmospheric dynamics. Some researchers propose that the storm's stability is tied to the planet's internal heat, which drives its weather systems and helps maintain the hexagonal structure. But the mystery doesn't end there. The storm also provides a window into Saturn's deeper atmospheric layers. By studying its behavior, scientists can learn more about the planet's wind speeds, temperature gradients, and even the composition of its clouds. The Cassini spacecraft, which captured stunning images of the storm during its mission, revealed intricate details about its structure, including a massive hurricane-like vortex at its center. This vortex, spinning at incredible speeds, adds another layer of complexity to the storm's dynamics. So, what does this bizarre storm tell us about Saturn as a whole? It highlights the planet's unique atmospheric conditions, shaped by its rapid rotation and internal heat. It also underscores the diversity of weather patterns in our solar system, from Jupiter's Great Red Spot to Saturn's hexagonal storm. Each of these phenomena offers a glimpse into the complex forces that govern the giant planets and their turbulent atmospheres. As we continue to study Saturn's hexagonal storm, we're reminded of the many mysteries that still surround this ringed giant. What other secrets might its swirling clouds hold, and how will they deepen our understanding of the outer planets? The answers lie in the winds of Saturn's north pole, where a six-sided storm continues to defy explanation and captivate our curiosity. Now turning to another celestial oddity, we set our sights on Uranus, the ice giant with a peculiar quirk. It rotates on its side. Unlike most planets in our solar system, which spin like tops with their axes roughly perpendicular to their orbits, Uranus is tilted at an extreme angle of about 98 degrees. This means its poles are almost where its equator should be, giving it the appearance of rolling around the Sun rather than spinning upright. But how did Uranus end up in such a unique position, and what does this mean for the planet itself? The leading theory suggests that Uranus's unusual tilt is the result of a cataclysmic collision with a massive object early in its history. Imagine a protoplanet, perhaps as large as Earth, slamming into Uranus with such force that it knocked the planet onto its side. This colossal impact would have not only altered Uranus's rotation, but also left lasting effects on its internal structure and magnetic field. Some scientists even speculate that the collision could have contributed to the planet's icy composition, as debris from the impact may have mixed with its atmosphere and interior. This extreme tilt has profound implications for Uranus's seasons and weather patterns. Each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness as the planet orbits the Sun. This creates some of the most extreme seasonal changes in the solar system, with temperatures and atmospheric conditions shifting dramatically over time. The planet's magnetic field is equally unusual, as it is both tilted and offset from its center, unlike the more aligned fields of Earth or Jupiter. This suggests that Uranus's internal dynamo, the process that generates its magnetic field, operates in a way that's still not fully understood. Comparing Uranus to other planets highlights just how unique it is. While Earth's axial tilt of about 23.5 degrees gives us our familiar seasons, Uranus's near 90-degree tilt creates a world where the concept of seasons is turned on its head. Even Saturn, with its 27-degree tilt, seems almost normal in comparison. This stark difference raises questions about the formation and evolution of the solar system. Was Uranus's collision a rare event, or could similar impacts have shaped other planets in ways we're only beginning to uncover? As we continue to study Uranus, its tilted axis serves as a reminder of the chaotic and dynamic processes that shaped our solar system. What other secrets might this ice giant hold, and how will they deepen our understanding of planetary formation and evolution? The answers lie in the windswept clouds of Uranus, where a sideways spin continues to challenge our assumptions and inspire new discoveries. Now turning to Neptune, the distant blue giant, we uncover another enigma that has puzzled scientists for decades: its mysterious heat source. Unlike most planets, which primarily rely on the Sun for warmth, Neptune emits more heat than it receives from our star. This raises the question, where is all this extra energy coming from, and what does it mean for the planet's dynamic atmosphere? The leading explanation points to Neptune's internal heat, generated deep within its core. As the planet slowly contracts under its own gravity, it releases gravitational energy, which is converted into heat. This process, known as Kelvin-Helmholtz contraction, is thought to be the primary driver of Neptune's excess warmth. However, this alone doesn't fully account for the planet's heat output, suggesting that other mechanisms, such as radioactive decay or residual heat from its formation, might also play a role. This internal heat has a profound impact on Neptune's weather, fueling some of the most violent storms in the solar system. The planet's atmosphere is a swirling mix of hydrogen, helium, and methane, with winds reaching speeds of over 1,200 miles per hour faster than the speed of sound on Earth. These extreme conditions create massive storms like the famous Great Dark Spot, a colossal storm system observed by the Voyager 2 spacecraft in 1989. While this storm has since disappeared, others have taken its place, showcasing Neptune's ever-changing and turbulent atmosphere. The heat from within also contributes to the planet's striking blue color. Methane in Neptune's upper atmosphere absorbs red light from the Sun, reflecting blue light back into space. This, combined with the planet's active weather patterns, makes Neptune a visually stunning world, even from billions of miles away. Comparing Neptune to its sibling Uranus, which emits very little internal heat, highlights the uniqueness of this mystery. Both planets are similar in size and composition, yet Neptune's heat output is significantly higher. This disparity suggests that the processes shaping these ice giants are far more complex than we once thought. Could Neptune's heat be a remnant of its violent formation, or is there another, yet undiscovered, source at work? As we continue to study Neptune, its mysterious heat source serves as a reminder of how much we still have to learn about the outer reaches of our solar system. What other secrets might this distant giant hold, and how will they reshape our understanding of planetary science? The answers lie in the swirling storms and icy depths of Neptune, where heat and mystery collide in one of the solar system's most captivating enigmas. Now turning to Pluto, the distant dwarf planet, we encounter one of the most visually striking mysteries in the solar system, its heart-shaped region, known as Sputnik Planitia. This vast, bright plain, spanning over 1,000 miles across, has captivated scientists and space enthusiasts alike since its discovery by the New Horizons mission in 2015. But what exactly is this heart-shaped feature, and how did it come to be? Sputnik Planitia is believed to be a massive impact basin, formed billions of years ago when a colossal object collided with Pluto. Over time, this basin filled with nitrogen ice, creating the smooth, reflective surface we see today. The ice is so bright that it reflects nearly all the sunlight that hits it, making Sputnik Planitia one of the most reflective regions in the solar system. But the mystery doesn't end there. Why does this ice remain so pristine and bright, even after eons of exposure to the harsh conditions of space? One theory suggests that Pluto's thin atmosphere plays a key role. As nitrogen ice sublimates, turning directly from solid to gas, it rises into the atmosphere and then recondenses, falling back onto the surface. This continuous cycle of sublimation and condensation could help maintain the region's brightness, effectively resurfacing it over time. Additionally, the heart-shaped region's low elevation may act as a cold trap, collecting and preserving the nitrogen ice. But Sputnik Planitia isn't just a geological curiosity, it also holds clues to Pluto's internal structure. The basin's location near Pluto's equator suggests that it has influenced the dwarf planet's orientation, causing it to reorient itself so that the heart-shaped region faces away from Pluto's largest moon, Charon. This process, known as true polar wander, indicates that Sputnik Planitia is not just a surface feature but a significant mass anomaly, possibly due to a dense layer of water ice beneath the nitrogen ice. The New Horizons mission provided unprecedented views of this enigmatic region, revealing a surface marked by polygonal patterns and ridges, likely caused by the slow convection of nitrogen ice. These features suggest that Sputnik Planitia is geologically active, a surprising discovery for such a small, distant world. As we ponder the mysteries of Pluto's heart, we're reminded of how much we still have to learn about the outer reaches of our solar system. What other secrets might this icy dwarf planet hold, and how will they reshape our understanding of planetary formation and evolution? The answers lie in the frozen plains of Sputnik Planitia, where science and wonder meet in one of the solar system's most captivating landscapes. Now turning to the Kuiper Belt, a distant region of icy bodies beyond Neptune, we uncover a treasure trove of strange and fascinating objects that challenge our understanding of the solar system's early days. This vast expanse, home to dwarf planets like Pluto and countless smaller bodies, holds clues to the chaotic beginnings of our cosmic neighborhood. Among these icy relics, some of the most peculiar are the elongated objects and binary systems that defy our expectations. Take, for example, the elongated shape of Arakoth, a Kuiper Belt object visited by the New Horizons mission in 2019. Resembling two flattened spheres fused together, Arrokoth's unique structure suggests it formed through a gentle collision of two smaller bodies in the early solar system. This slow, low-speed merging process provides a snapshot of how planetesimals, the building blocks of planets, came together billions of years ago. Unlike the violent collisions we often imagine, Arrokoth's formation hints at a more delicate dance in the frigid outskirts of the solar system. But Arrokoth isn't the only oddity in the Kuiper belt. Binary systems where two objects orbit each other are surprisingly common in this region. These pairs, often referred to as binary Kuiper belt objects, raise intriguing questions about their origins. How did these objects come to orbit one another in such a distant and sparsely populated part of the solar system? One theory suggests that gravitational interactions in the early solar system nudged these objects into close proximity, allowing them to capture each other in a delicate gravitational embrace. Studying these binaries helps scientists piece together the conditions and dynamics of the solar system's infancy. The Kuiper belt's strange objects also offer insights into the migration of planets. Many of these icy bodies have orbits that are tilted or stretched, suggesting they were influenced by the gravitational pull of Neptune as it moved outward during the solar system's formation. This planetary migration likely scattered countless objects into the Kuiper belt, creating the diverse and eccentric population we see today. As we explore these distant, icy worlds, we're reminded that the Kuiper belt is more than just a collection of frozen debris. It's a time capsule preserving the early history of our solar system. What other secrets might these strange objects hold? And how will they reshape our understanding of the cosmic processes that shaped our home in the universe? The answers lie in the icy depths of the Kuiper belt, where every discovery brings us closer to unraveling the mysteries of our solar system's past. Now turning to the Oort cloud, we venture even farther into the outer reaches of our solar system, where a vast and mysterious shell of icy objects lies hidden in the darkness. This distant region, named after the Dutch astronomer Jan Oort, is believed to be the source of many long-period comets that occasionally streak into the inner solar system. But what exactly is the Oort cloud, and why is it so difficult to study? The Oort cloud is thought to be a spherical shell of icy bodies surrounding the solar system at a distance of up to 100,000 times farther from the Sun than Earth. Unlike the flat, disk-like Kuiper belt, the Oort cloud envelops the solar system in all directions, making it a true frontier of our cosmic neighborhood. These icy objects, remnants from the solar system's formation, are so far away that they remain almost entirely untouched by the Sun's warmth or gravitational influence. One of the most fascinating aspects of the Oort cloud is its role in delivering comets to the inner solar system. When a passing star or the gravitational tug of the Milky Way disturbs an object in the Oort cloud, it can be sent hurtling toward the Sun, becoming a long-period comet. These comets, with orbits lasting thousands or even millions of years, provide fleeting glimpses into the composition of the Oort cloud. Yet, because these objects spend most of their time in the distant reaches of space, studying them directly is an enormous challenge. The sheer distance of the Oort cloud makes it nearly impossible to observe directly with current technology. Even our most powerful telescopes struggle to detect these faint, icy bodies against the backdrop of interstellar space. Instead, scientists rely on indirect evidence, such as the trajectories and compositions of comets, to infer the Oort cloud's structure and contents. This has led to a hypothetical model of the Oort cloud as a vast reservoir of icy debris stretching halfway to the nearest star. But why does the Oort cloud exist in the first place? One theory suggests that it formed from icy materials scattered outward by the gravitational interactions of the giant planets during the solar system's early days. Over billions of years, these objects settled into the distant, spherical shell we now call the Oort cloud. Another possibility is that some of these icy bodies were captured from other star systems during close encounters in the Sun's infancy. As we ponder the mysteries of the Oort cloud, we're reminded of how much of our solar system remains unexplored. What other secrets might this distant region hold, and how will future missions and technologies bring us closer to understanding it? The Oort cloud stands as a testament to the vastness and complexity of our cosmic home, inviting us to keep looking outward and uncovering the hidden stories of the universe. Now turning to the Sun, we uncover one of the most perplexing mysteries in our solar system: why the Sun's corona, its outer atmosphere, is so much hotter than its surface. At first glance, this seems counterintuitive. The Sun's surface, or photosphere, burns at around 5,500 degrees Celsius, but the corona, which lies millions of kilometers above, reaches temperatures of over 1 million degrees Celsius. How can the outer layer of the Sun be hundreds of times hotter than the surface itself? This question has puzzled scientists for decades, and while we've made progress, the answer remains elusive. One leading theory points to the Sun's magnetic fields as the key to this mystery. The Sun is a dynamic, churning ball of plasma, and its magnetic fields are constantly twisting, breaking, and reconnecting. These magnetic interactions are thought to release enormous amounts of energy, heating the corona to extreme temperatures. Imagine a tangled web of magnetic lines, snapping and reconnecting like rubber bands, sending bursts of energy outward. This process, known as magnetic reconnection, could be the engine driving the corona's intense heat. Another theory involves the role of solar winds and waves. The Sun's surface is a turbulent place with waves of energy constantly rippling outward. Some scientists believe that these waves, particularly a type called Alfvén waves, carry energy from the Sun's interior to the corona. As these waves travel through the Sun's magnetic fields, they could transfer their energy to the corona, heating it up in the process. Think of it like a guitar string vibrating and transferring energy to the air around it, but on a cosmic scale. The mystery of the Sun's corona is not just an academic curiosity. Understanding it has real implications for space, weather, and its effects on Earth. Solar flares and coronal mass ejections, which originate in the corona, can disrupt satellites, power grids, and communication systems. By unraveling the secrets of the corona, we can better predict and mitigate these potentially devastating events. Visuals of the Sun's corona during a solar eclipse provide some of the most striking evidence of its beauty and complexity. During an eclipse, the Moon blocks the Sun's bright surface, revealing the faint, wispy tendrils of the corona stretching outward into space. These images not only captivate us but also offer valuable clues about the corona's structure and behavior. As we continue to study the Sun, we're reminded of how much we still have to learn about our closest star. What other secrets does the corona hold, and how will future missions like the Parker Solar Probe bring us closer to solving this mystery? The Sun's corona stands as a fiery enigma, challenging us to unlock the secrets of its extraordinary heat. Now turning to the Moon, we encounter another fascinating mystery. Why did the Moon once have a magnetic field, and why did it vanish? Today, the Moon is a quiet, airless world with no global magnetic field, but billions of years ago it was a very different place. Evidence from lunar rocks brought back by the Apollo missions shows that the Moon once had a magnetic field, possibly even stronger than Earth's is today. So, what happened to it? The key to this mystery lies deep within the Moon's core. Scientists believe that the Moon's magnetic field was generated by a dynamo effect, similar to how Earth's magnetic field is created. This process involves the movement of molten metal in a planet's core, which generates electric currents and, in turn, a magnetic field. For the Moon, this dynamo would have required a molten, churning core, likely powered by the heat left over from its formation and the energy released by radioactive elements. But why did the dynamo stop? One theory suggests that as the Moon cooled over time, its core solidified, shutting down the dynamo and causing the magnetic field to fade. Another possibility is that the Moon's core was kept molten by tidal forces from Earth's gravity. But as the moon gradually moved farther away from Earth, these forces weakened, allowing the core to cool and the dynamo to cease. Imagine a spinning top slowly losing momentum until it finally comes to a stop. That's what might have happened to the moon's magnetic field. The disappearance of the moon's magnetic field also raises questions about its early history. A strong magnetic field would have protected the moon from the solar wind, potentially preserving its atmosphere and surface water. Without it, the moon became the barren, desolate world we see today. This mystery not only sheds light on the moon's past, but also helps us understand how other small, rocky bodies in the solar system evolve over time. Visuals of the moon's surface and simulations of its ancient magnetic field offer a glimpse into this lost chapter of lunar history. These images show us a moon that was once dynamic and active, a stark contrast to the silent, cratered landscape we see today. As we continue to study the moon, missions like NASA's Artemis program aim to uncover more clues about its magnetic past and what it means for the future of lunar exploration. The moon's magnetic field remains a captivating puzzle, reminding us that even our closest celestial neighbor holds secrets waiting to be uncovered. What other surprises does the moon have in store, and how will they reshape our understanding of its history? As we look to the skies, the moon continues to inspire curiosity and wonder, challenging us to explore its mysteries further. Now turning to Mars, we encounter another intriguing mystery: the origins of its two small moons, Phobos and Deimos. These irregularly shaped moons have puzzled scientists for decades, raising questions about how they came to orbit the red planet. Unlike Earth's moon, which formed from a giant impact, Phobos and Deimos have a much more enigmatic history. So, how did these Martian moons come to be? One leading theory suggests that Phobos and Deimos are captured asteroids. Mars, located near the asteroid belt, could have gravitationally pulled in these objects as they drifted too close. This idea is supported by the moon's appearance, which resembles that of many asteroids, dark, cratered, and irregular in shape. However, there's a catch. The orbits of Phobos and Deimos are nearly circular and aligned with Mars's equator, which is unusual for captured objects. Typically, captured asteroids have more eccentric and tilted orbits, making this theory a bit harder to fully explain. Another possibility is that the moons formed from debris left over after a massive impact on Mars. Similar to how Earth's moon is thought to have formed, a collision between Mars and a large object could have ejected material into orbit, which later coalesced into Phobos and Deimos. This theory would explain their circular orbits and alignment with Mars's equator. However, the moon's composition, which is more similar to asteroids than to Mars itself, complicates this idea. If they formed from Martian debris, why don't they share more of the planet's characteristics? Adding to the mystery is the fate of Phobos. This moon is slowly spiraling inward toward Mars and is expected to either crash into the planet or break apart into a ring of debris in about 50 million years. Deimos, on the other hand, is gradually moving away. These contrasting trajectories suggest that the moons have different histories, further complicating the puzzle of their origins. Visuals of Phobos and Deimos, along with simulations of their orbits, provide a fascinating glimpse into these enigmatic moons. Their small size and irregular shapes make them look almost like cosmic potatoes, but their story is anything but simple. As we continue to study Mars and its moons, missions like Japan's Martian Moons Exploration, or MMX, aim to collect samples from Phobos and bring them back to Earth. These samples could hold the key to unlocking the mystery of how these moons formed and what they can tell us about the early solar system. The origins of Phobos and Deimos remain a captivating enigma, reminding us that even the smallest objects in our solar system can hold profound secrets. What will we discover about these Martian moons, and how will their story reshape our understanding of Mars's history? As we look to the future, the mysteries of Phobos and Deimos continue to inspire exploration and curiosity, challenging us to uncover the truth hidden in their ancient orbits. Now turning to Saturn, we encounter one of the most breathtaking sights in our solar system, its magnificent rings. But these dazzling rings are more than just a visual marvel. They hold a mystery that has puzzled scientists for centuries. How old are Saturn's rings, and why do they shine so brightly? For a long time, astronomers believed Saturn's rings were as old as the planet itself, forming around 4.5 billion years ago alongside the rest of the solar system. However, recent data from the Cassini spacecraft has turned this idea on its head. The rings appear to be much younger, possibly only a few 100 million years old. This raises a fascinating question. If the rings are so young, how did they form so recently in the grand timeline of the solar system? One theory suggests that the rings are the remnants of a shattered moon or comet. A catastrophic collision or a close encounter with Saturn's gravity could have torn apart a passing object, scattering its debris into orbit. Over time, this debris settled into the thin, bright rings we see today. The brightness of the rings supports this idea, as fresh ice reflects sunlight more effectively than older, dust-covered surfaces. But if this is true, why don't we see similar rings around other gas giants like Jupiter or Neptune? Another possibility is that the rings are constantly being replenished. Tiny moonlets within the rings, known as shepherd moons, might be breaking apart due to tidal forces, releasing fresh material that keeps the rings bright and youthful. This ongoing process could explain why the rings appear so vibrant despite their relatively young age. But the mystery doesn't end there. Saturn's rings are also disappearing. Tiny particles from the rings are slowly raining down onto the planet, a process known as ring rain. Scientists estimate that the rings could vanish entirely in the next 100 million years. This fleeting nature adds another layer of intrigue. Are we witnessing a rare cosmic event, or is this a common occurrence in the life of a gas giant? Visuals from the Cassini mission provide stunning details of Saturn's rings, showcasing their intricate structure and icy brilliance. From the massive gaps created by shepherd moons to the delicate ripples caused by passing comets, these images reveal a dynamic and ever-changing system. The age and brightness of Saturn's rings remain a captivating puzzle, reminding us that even the most familiar features of our solar system can hold surprising secrets. What will future missions reveal about the origins and fate of these iconic rings? As we continue to explore Saturn, the story of its rings challenges us to rethink our understanding of planetary systems and their evolution. Now turning to the ice giants Uranus and Neptune, we uncover another layer of mystery in our solar system: their bizarre magnetic fields. Unlike Earth, where the magnetic field aligns closely with the planet's rotational axis, the magnetic fields of Uranus and Neptune are tilted and offset in ways that defy easy explanation. What could cause such unusual behavior in these distant worlds? Let's start with Uranus. Its magnetic field is tilted at an extreme angle of about 60 degrees from its rotational axis. To put that into perspective, imagine if Earth's magnetic North Pole were located somewhere near Florida instead of the Arctic. This strange tilt suggests that Uranus's magnetic field isn't generated in the same way as Earth's, where the dynamo effect in the molten iron core creates a relatively stable field. Instead, scientists believe that Uranus's magnetic field might originate from a layer of electrically conductive material, possibly a slushy mix of water, ammonia, and methane deep within its icy interior. But why is this layer so asymmetrical, and what caused the magnetic field to tilt so dramatically? One theory points to a massive collision in Uranus's past, which not only knocked the planet onto its side but also disrupted its internal structure, creating the conditions for this peculiar magnetic field. Neptune, on the other hand, has a magnetic field that's not only tilted but also offset from the planet's center. Its magnetic axis is shifted by about half the planet's radius, meaning the magnetic field doesn't even originate from the core. This offset is even more pronounced than Uranus's, and it raises questions about the internal dynamics of Neptune. Like Uranus, Neptune's magnetic field is thought to be generated in a layer of conductive material, but the exact nature of this layer remains a mystery. Could it be a result of the planet's extreme pressures and temperatures, or is there another process at work that we haven't yet discovered? Comparing these ice giants to Earth highlights just how unique their magnetic fields are. Earth's magnetic field is relatively straightforward, generated by the motion of molten iron in its core. But Uranus and Neptune challenge our understanding of planetary magnetism, showing that not all magnetic fields are created equal. Their tilted and offset fields suggest that the interiors of these planets are far more complex than we once thought, with layers of material behaving in ways we're only beginning to comprehend. Visuals from spacecraft missions like Voyager 2, which flew by both Uranus and Neptune in the 1980s, provide glimpses of these magnetic fields in action. These images reveal the chaotic and asymmetrical nature of the fields, with magnetic lines looping and twisting in unexpected patterns. They also show how these fields interact with the solar wind, creating auroras that are far more irregular than the ones we see on Earth. The magnetic fields of Uranus and Neptune remain one of the most intriguing mysteries in our solar system. What do they tell us about the hidden interiors of these distant worlds? And how do they influence the planet's atmospheres and weather patterns? As we continue to study these ice giants, their magnetic fields challenge us to rethink our understanding of planetary formation and evolution. What secrets will future missions uncover about these enigmatic giants? Now turning to the asteroid belt, we encounter one of the most puzzling features in our solar system, the bright spots on Ceres. As the largest object in the asteroid belt, Ceres has long fascinated scientists, but its mysterious bright spots have sparked even more intrigue. These dazzling patches, first observed by NASA's Dawn spacecraft, stand out starkly against the dwarf planet's otherwise dark and cratered surface. What could be causing these luminous areas, and what do they reveal about Ceres' composition and history? The most prominent of these bright spots lies within Ocata crater, a massive impact site spanning nearly 60 miles in diameter. At the center of the crater, a cluster of reflective patches shines with an intensity that baffled researchers when they were first discovered. Early theories suggested that these spots could be made of ice, reflecting sunlight like a cosmic mirror. However, further analysis revealed that the bright material is more likely composed of salts, specifically a type of magnesium sulfate called hexahydrite. These salts are thought to have been left behind as briny water from beneath Ceres' surface evaporated into space, leaving behind a gleaming residue. But how did this brine reach the surface? One leading theory proposes that Ceres has a subsurface reservoir of salty water, possibly even a global ocean hidden beneath its icy crust. Impacts from asteroids or comets could have fractured the crust, allowing the brine to seep upward and form the bright spots we see today. This idea is supported by the presence of other geological features on Ceres, such as domes and fractures, which suggest that the dwarf planet has experienced significant internal activity. If true, Ceres could join the ranks of icy moons like Europa and Enceladus as a potential candidate for harboring liquid water, and perhaps even the conditions necessary for life. Another intriguing aspect of Ceres' bright spots is their variability. Observations have shown that the brightness of these spots changes over time, possibly due to the sublimation of ice or the exposure of fresh salt deposits. This dynamic behavior hints at an active, evolving surface, challenging the notion that small bodies like Ceres are static and unchanging. Instead, Ceres appears to be a world with a complex and ongoing geological history, shaped by both internal and external forces. Visuals from the Dawn mission provide stunning close-ups of these bright spots, revealing intricate details about their structure and composition. These images show the spots surrounded by darker material, creating a striking contrast that highlights their brilliance. They also capture the rugged terrain of Akata crater, with its steep walls and central dome, offering clues about the forces that shaped this enigmatic landscape. The mystery of Ceres' bright spots is far from solved. Are they the remnants of an ancient ocean, or do they point to a more recent geological process? What role do impacts and internal activity play in shaping Ceres' surface? And could these bright spots hold clues about the potential for life in the asteroid belt? As we continue to study Ceres, its gleaming patches remind us that even the smallest worlds in our solar system can hold some of the biggest surprises. What other secrets might this dwarf planet reveal as we delve deeper into its mysteries? Now turning to the outer reaches of our solar system, we encounter a group of celestial objects that defy expectations, the trans-Neptunian objects. These icy bodies, located beyond the orbit of Neptune, follow paths that are anything but ordinary. Some of these objects have orbits that are highly elongated, tilted at extreme angles, or clustered in ways that seem impossible to explain by the gravitational influence of the known planets alone. What could be causing these strange orbital patterns, and what do they reveal about the hidden dynamics of our solar system? One of the most compelling theories to explain these unusual orbits is the existence of a yet undiscovered planet, often referred to as Planet 9. This hypothetical world, estimated to be about 10 times the mass of Earth, could be lurking in the distant reaches of the solar system, exerting a gravitational pull strong enough to warp the orbits of smaller objects. The idea of Planet 9 emerged when astronomers noticed that several trans-Neptunian objects shared similar orbital characteristics, such as clustering on one side of the Sun and having orbits tilted in the same direction. These patterns suggest that a massive object could be shepherding them into these unusual paths, but Planet 9 isn't the only possible explanation. Some scientists propose that the strange orbits could be the result of gravitational interactions with other large objects, such as rogue planets or even a passing star that disrupted the solar system billions of years ago. Others suggest that the collective gravitational influence of many smaller objects in the Kuiper belt could gradually alter the orbits of trans-Neptunian objects over time. Each of these theories offers a unique perspective on the forces shaping the outer solar system, but none have been definitively proven. Visuals of these distant objects and their orbits provide a fascinating glimpse into this mysterious region. Images from telescopes show the faint, icy bodies as they travel along their peculiar paths, often appearing as mere specks of light against the vastness of space. Simulations of their orbits reveal the complex dance of gravity that could be at play, with some objects looping far out into the darkness before swinging back toward the Sun. These visuals not only highlight the strangeness of these orbits, but also underscore the challenges of studying objects so far from Earth. The mystery of the trans-Neptunian objects' orbits raises profound questions about the history and structure of our solar system. Could Planet 9 really exist, and if so, how has it remained hidden for so long? What other unseen forces might be influencing these distant worlds? And what do these strange orbits tell us about the early days of the solar system, when planets and smaller bodies were still forming and jostling for position? As we continue to explore the outer reaches of our cosmic neighborhood, these enigmatic objects remind us that there is still much to discover about the forces that shape our solar system. What other surprises might be waiting for us in the distant, icy realms beyond Neptune? Now turning to our closest celestial neighbor, the Moon, we uncover a mystery that has fascinated scientists and explorers alike: the presence of water ice. For decades, the Moon was thought to be a dry, barren world, but recent discoveries have revealed that water ice exists in significant quantities, particularly at the lunar poles. This revelation has profound implications for our understanding of the Moon and its potential as a resource for future exploration. the discovery of water ice on the Moon came as a surprise to many. Early missions, including the Apollo program, found no direct evidence of water, leading to the assumption that the Moon was completely dry. However, in the late 1990s, data from the Lunar Prospector mission suggested the presence of hydrogen, a key component of water, in the permanently shadowed craters at the Moon's poles. This finding was later confirmed by more advanced missions, such as the Lunar Reconnaissance Orbiter and India's Chandrayaan-1, which detected definitive signs of water ice in these regions. But where does this water ice come from? One theory suggests that it was delivered by comets and asteroids that bombarded the Moon over billions of years. These icy bodies could have deposited water molecules on the lunar surface, which then migrated to the coldest regions, the permanently shadowed craters at the poles. Another possibility is that the water was formed through interactions between the solar wind and the Moon's surface. The solar wind, a stream of charged particles from the Sun, could have reacted with oxygen-bearing minerals in the lunar soil to produce water molecules. The presence of water ice on the Moon has exciting implications for future exploration. Water is not only essential for human survival, but can also be broken down into hydrogen and oxygen, which can be used as rocket fuel. This means that the Moon could serve as a refueling station for missions to Mars and beyond, significantly reducing the cost and complexity of deep space exploration. Additionally, the water ice could support the establishment of lunar bases, providing a sustainable resource for astronauts living and working on the Moon. Visuals of the Moon's poles reveal the stark, shadowy craters where water ice is believed to reside. These regions, never touched by sunlight, are some of the coldest places in the solar system, with temperatures plunging to hundreds of degrees below zero. Images from lunar missions show the rugged terrain of these craters, with their steep walls and dark interiors, offering a glimpse into the hidden reservoirs of ice that lie within. The mystery of the Moon's water ice raises important questions about the history and evolution of our solar system. How did water, a key ingredient for life, end up on the Moon? What other resources might be hidden in the lunar soil? And how can we harness these resources to advance our exploration of space? As we prepare to return to the Moon with ambitious missions like NASA's Artemis program, the discovery of water ice reminds us that even our closest neighbor still holds secrets waiting to be uncovered. What other surprises might the Moon have in store for us as we venture back to its surface? Now turning to the heart of our solar system, we encounter a mystery that has puzzled scientists for decades: the case of the Sun's missing neutrinos. Neutrinos are tiny, nearly massless particles produced in vast quantities by nuclear reactions in the Sun's core. They stream out into space, passing through matter almost effortlessly, including the Earth itself. Yet, when scientists began detecting these elusive particles, they found something unexpected. Far fewer neutrinos were being detected than the Sun's physics predicted. This discrepancy became known as the solar neutrino problem, and it has since become one of the most intriguing puzzles in astrophysics. The mystery began in the 1960s, when the first neutrino detectors were built to observe these particles. Experiments like the Homestake detector, buried deep underground to shield it from other cosmic particles, consistently detected only about 1/3 of the neutrinos predicted by theoretical models of the Sun's core. This raised a critical question: where were the missing neutrinos? For years, scientists debated whether the problem lay in our understanding of the Sun or in the nature of neutrinos themselves. The breakthrough came with the discovery of neutrino oscillations, a phenomenon where neutrinos change their flavor as they travel through space. Neutrinos come in 3 types or flavors: electron, muon, and tau, and early detectors were only sensitive to electron neutrinos. It turned out that the missing neutrinos weren't missing at all. They had simply transformed into muon and tau neutrinos, which the original detectors couldn't detect. This discovery not only solved the solar neutrino problem, but also revealed that neutrinos have mass, a finding that has profound implications for particle physics and our understanding of the universe. The Sun's core, where these neutrinos are born, is a seething cauldron of nuclear fusion. Temperatures soar to millions of degrees, and immense pressure forces hydrogen atoms to fuse into helium, releasing energy in the process. This energy powers the Sun and, by extension, life on Earth. Visuals of the Sun's core, based on simulations and data from solar observatories, show the intense, chaotic environment where neutrinos are produced. Meanwhile, images of neutrino detectors like the massive Super Kamiok and in Japan highlight the ingenuity of scientists in capturing these ghostly particles. The mystery of the Sun's missing neutrinos has reshaped our understanding of both the Sun and the fundamental nature of matter. It underscores the importance of questioning our assumptions and the power of scientific inquiry to uncover hidden truths. As we continue to study the Sun and its neutrinos, we gain deeper insights into the processes that power our star and the universe at large. What other secrets might the Sun hold, waiting to be revealed by the next generation of detectors and experiments? Now turning to Saturn's largest moon, Titan, we encounter a mystery that has fascinated scientists for decades: the abundance of methane on its surface. Titan is unique in our solar system, as it is the only moon with a dense atmosphere and liquid lakes on its surface. But these aren't lakes of water. They're filled with methane and ethane, making Titan a world of hydrocarbon seas. The question is, why does Titan have so much methane, and how is it being replenished? Methane is a key player in Titan's atmosphere and surface processes. On Earth, methane is a gas, but on Titan, the frigid temperatures allow it to exist as a liquid. This methane forms vast lakes and rivers, creating a landscape that eerily resembles Earth's hydrologic cycle, but with hydrocarbons instead of water. However, methane is not stable in Titan's atmosphere. Over time, sunlight breaks it down into other compounds, which eventually rain down onto the surface. This means that Titan's methane should have been depleted long ago, yet it remains abundant. So, where is all this methane coming from? Scientists have proposed several theories to explain this mystery. One possibility is that Titan has an internal reservoir of methane stored beneath its icy crust. This methane could be released through cryovolcanism, where icy volcanoes erupt and spew methane into the atmosphere. Another theory suggests that Titan's methane is being replenished by cometary impacts, which deliver fresh methane to the surface. However, neither of these explanations fully accounts for the sheer volume of methane observed. The presence of methane also raises intriguing questions about Titan's potential for life. While the Moon's surface is far too cold for liquid water, some scientists speculate that life could exist in its methane lakes or beneath its icy crust, where liquid water might be present. The Cassini spacecraft, which explored Titan during its mission, provided stunning visuals of its hazy atmosphere, methane lakes, and rugged terrain. These images have fueled our curiosity about this enigmatic moon and its potential to harbor life. As we continue to study Titan, the mystery of its methane remains a tantalizing puzzle. Future missions like NASA's Dragonfly rotorcraft aim to explore Titan's surface in greater detail, potentially uncovering clues about its methane cycle and the possibility of life. What secrets might Titan hold beneath its thick, orange haze? The answers could reshape our understanding of this distant moon and its place in the solar system. Now turning to Europa, one of Jupiter's most intriguing moons, we uncover a mystery that has captivated scientists and dreamers alike: the possibility of a vast, hidden ocean beneath its icy crust. Europa's surface is a frozen, cracked landscape, but beneath this icy shell lies what many believe to be a global ocean of liquid water. This discovery has sparked questions about the potential for life beyond Earth, making Europa one of the most promising targets in the search for extraterrestrial life. The evidence for Europa's subsurface ocean comes from several key observations. First, images from spacecraft like Galileo reveal a surface covered in fractures and ridges, suggesting that the ice is floating on a liquid layer below. Second, measurements of Europa's magnetic field indicate the presence of a conductive material, likely salty water, beneath the ice. Finally, plumes of water vapor have been detected erupting from Europa's surface, hinting at the ocean's presence and its interaction with the icy shell above. But what makes this ocean so fascinating is its potential habitability. On Earth, life thrives in the most extreme environments, from deep-sea hydrothermal vents to Antarctic ice. Europa's ocean, warmed by tidal forces generated by Jupiter's immense gravity, could provide the energy and nutrients needed to sustain microbial life. The presence of water, combined with the possibility of organic molecules, makes Europa a prime candidate for harboring life in our solar system. Future missions aim to explore Europa in greater detail, seeking answers to these profound questions. NASA Europa Clipper, set to launch in the coming years, will conduct detailed reconnaissance of the Moon's ice shell and subsurface ocean. It will search for signs of recent geological activity and analyze the composition of the plumes erupting from the surface. Even more ambitious plans, like a potential lander mission, could one day drill through the ice to directly sample the ocean below. As we peer into the mysteries of Europa, we are reminded of how much we have yet to learn about the worlds beyond our own. Could this icy moon with its hidden ocean be home to the first signs of extraterrestrial life? The answers lie beneath the ice, waiting to be uncovered. With each new mission, we move closer to solving the enigma of Europa's ocean and perhaps rewriting our understanding of life in the universe. Now turning to Venus, we encounter a world of extremes where the weather defies everything we know about planetary atmospheres. Venus, often called Earth's twin due to its similar size, is anything but familiar when it comes to its climate. The planet's atmosphere is a swirling, chaotic mess, dominated by superrotation, a phenomenon where the atmosphere spins much faster than the planet itself. While Venus takes 243 Earth days to complete one rotation, its atmosphere whips around the planet in just 4 Earth days. This bizarre behavior has left scientists puzzled for decades. The winds on Venus are relentless, reaching speeds of up to 220 miles per hour, far faster than any hurricane on Earth. These high-speed winds create a global circulation pattern that pushes the thick, toxic clouds of sulfuric acid around the planet in a never-ending cycle. The clouds themselves are another mystery. They form a dense, reflective layer that traps heat, contributing to Venus's runaway greenhouse effect and making it the hottest planet in the solar system, with surface temperatures hot enough to melt lead. But what drives this super-rotation? One theory suggests that the intense heat from the Sun, combined with Venus's slow rotation, creates a pressure difference that powers the fast-moving winds. Another idea points to the planet's thick atmosphere, which acts like a giant flywheel, storing and transferring energy to keep the winds in motion. Despite decades of study, the exact mechanisms behind Venus's extreme weather remain unclear. Adding to the mystery are the planet's sulfuric acid clouds, which are not only corrosive but also highly reflective, giving Venus its brilliant appearance in the night sky. These clouds are constantly replenished by volcanic activity, which releases sulfur dioxide into the atmosphere. Over time, this gas reacts with sunlight to form sulfuric acid droplets, creating the dense cloud cover that shrouds the planet. Future missions like NASA proposed Veritas and Da Vinci Plus aim to unravel the secrets of Venus's atmosphere. By studying its weather patterns, composition, and surface interactions, scientists hope to gain a better understanding of how such extreme conditions arise and persist. Venus serves as a stark reminder of how different a planet can be from its Earth-like beginnings, offering valuable insights into the forces that shape planetary climates. As we explore the strange weather of Venus, we are reminded of the complexity and diversity of our solar system. What drives the super-rotation of its atmosphere? How do the sulfuric acid clouds form and persist? These questions challenge our understanding of planetary science and push us to uncover the secrets hidden within this enigmatic world. Now turning to Jupiter's moon Io, we encounter a world of fire and fury, unlike anything else in our solar system. Io is the most volcanically active body we know of, with hundreds of volcanoes dotting its surface, some of which spew lava dozens of miles into the sky. This intense activity has transformed Io into a landscape of molten rock, towering mountains, and vast lava plains, making it a geological wonder and a mystery that continues to captivate scientists. So, what makes Io so volcanic? The answer lies in its relationship with Jupiter and its neighboring moons. Io is caught in a gravitational tug of war between Jupiter's immense pull and the gravitational forces from nearby moons like Europa and Ganymede. These tidal forces stretch and squeeze Io's interior, generating immense heat through friction. This heat melts Io's rocky mantle, creating vast reservoirs of magma that fuel its constant eruptions. It's like squeezing a stress ball over and over. Eventually, something has to give, and for Io, that means volcanic explosions on a massive scale. The scale of Io's volcanic activity is staggering. Some of its eruptions are so powerful that they can be seen from Earth with powerful telescopes. The lava flows on Io are hotter than any found on Earth, with temperatures reaching up to 2,000 degrees Fahrenheit. These flows reshape the moon's surface, creating new features and burying old ones in a matter of years. Unlike Earth, where volcanic activity is driven by the movement of tectonic plates, Io's volcanoes are powered entirely by the tidal forces acting on its interior. But Io's volcanic activity isn't just a spectacle, it also provides clues about the moon's interior. Scientists believe that beneath its fiery surface lies a partially molten core, surrounded by a mantle of molten rock. The constant tidal heating keeps this interior in a state of turmoil, ensuring that Io remains a hotbed of volcanic activity. Studying Io's volcanoes helps us understand not only this moon, but also the processes that shape other worlds, including those beyond our solar system. Future missions like NASA-planned Europa Clipper may provide new insights into Io's volcanic mysteries. By studying the gravitational interactions between Jupiter and its moons, scientists hope to better understand how tidal forces drive Io's extreme geology. Io serves as a reminder of the dynamic and ever-changing nature of our solar system, where even a small moon can hold secrets that challenge our understanding of planetary science. As we explore the fiery world of Io, we are left with questions that push the boundaries of our knowledge. What drives the immense heat within its interior? How do its volcanoes shape its surface over time? These mysteries remind us that even in the cold reaches of space, there are worlds that burn with activity, waiting to reveal their secrets. Now turning to Saturn's moon Enceladus, we encounter a world that gleams like a cosmic diamond in the darkness of space. Enceladus is one of the brightest objects in our solar system, reflecting almost 100% of the sunlight that hits its surface. This extraordinary brightness is due to its icy shell, which is covered in a layer of fresh, clean ice that acts like a giant mirror. But what makes Enceladus so bright, and what lies beneath its shimmering surface? The secret to Enceladus's brilliance lies in its active geology. Unlike many other icy moons, Enceladus isn't just a frozen, lifeless world. It's a place of constant renewal where geysers of water and ice erupt from its south pole, spewing material hundreds of miles into space. These plumes, first discovered by the Cassini spacecraft, are fed by a global ocean of liquid water hidden beneath the moon's icy crust. As the water erupts, it freezes into tiny ice particles, which then fall back onto the surface, creating a fresh, reflective layer that keeps Enceladus gleaming. The geysers of Enceladus are more than just a stunning spectacle, they're a window into the moon's interior. Scientists believe that the ocean beneath the ice is kept warm by tidal forces, similar to those that heat Io. Saturn's gravity stretches and squeezes Enceladus, generating enough heat to keep the water liquid and drive the geysers. This makes Enceladus one of the most promising places in the solar system to search for signs of life. The plumes contain not just water but also organic molecules, the building blocks of life, making this icy moon a prime target for future exploration. The Cassini mission provided us with breathtaking images of Enceladus's plumes, revealing their complexity and beauty. These plumes create a faint ring around Saturn, known as the E-ring, which is made up of the tiny ice particles ejected by Enceladus. This connection between the moon and its planet highlights the dynamic interactions that shape our solar system. Enceladus's brightness isn't just a surface feature, it's a sign of the moon's active interior and its potential to harbor life. As we marvel at the icy brilliance of Enceladus, we are left with questions that challenge our understanding of this distant world. What keeps its ocean liquid? Could life exist in its hidden depths? These mysteries remind us that even in the cold, dark reaches of space, there are worlds that shine with possibility, waiting to reveal their secrets. Now turning to the conclusion of our journey through the 25 unsolved mysteries of the solar system, we are reminded of just how vast and enigmatic our cosmic neighborhood truly is. From the dark side of Mercury to the icy plumes of Enceladus, each mystery we've explored reveals a piece of the puzzle that is our solar system, a puzzle that is far from complete. These unanswered questions highlight not only the limits of our current knowledge, but also the boundless potential for discovery that lies ahead. As we reflect on these mysteries, one thing becomes clear: the solar system is a place of endless wonder. Whether it's the strange weather on Venus, the missing planet between Mars and Jupiter, or the hidden ocean beneath Europa's icy crust, each enigma challenges us to think deeper, explore further, and question what we think we know. These mysteries are not just scientific curiosities, they are invitations to push the boundaries of human understanding and to uncover the secrets that the universe has yet to reveal. So, what do you think? Which of these mysteries fascinates you the most? Could it be the shrinking great red spot of Jupiter, the hexagonal storm on Saturn, or perhaps the possibility of life in the subsurface oceans of distant moons? Let us know in the comments below. We'd love to hear your thoughts and theories. And if you've enjoyed this journey through the unsolved mysteries of the solar system, don't forget to subscribe and hit the notification bell so you never miss an update. There's so much more to explore, and we're just getting started. Until next time, keep looking up. The cosmos is waiting.